Hi everyone. I'm trying to do a little demonstration for our tutorial of electric field and flux. On the first page, for exercise of area vector, they're asking you to describe like a vector which you can connect to the flat piece of paper with area A. So, well, this is like piece of paper. Okay, give me a second. I'll turn off the lights. It's too bright, I guess. That's a large piece of paper. And the area vector you can, well, relate to this area. It's a vector which looks like this, like a perpendicular to the flat sheet, and the magnitude of this vector is supposed to be equal to the area of the piece of paper. Well, bigger piece of paper, bigger area. They're asking what is going to be the magnitude of delta area if you want to connect a little vector with every square on this paper. Well, the magnitude is going to be much smaller, right? Depending on like area of this little square is going to be like a tiny small vector pointing out of the square. It's supposed to be perpendicular to the flat piece of paper because any other direction is not going to show you direction of the page. Only perpendicular direction shows you like, okay, page was perpendicular, so you can always find it, okay? Then they're asking you to make a triangle or a prism out of this paper. I'm going to do it, but let's say I'm not super good, and they're asking you what kind of vectors you can connect to this prism. Like, well, remember that we always connect area vector with something flat. So here we do have 3 flat sides, so maybe you can count how many vectors we'll need to connect to each side, all right? And last question on the first page, they're asking you to make a, let's say, cylindrical shape. Sorry, I have just one piece of paper which is squared. All my other paper is lined at home. So something like a cylindrical shape looking like this. And they're asking you to describe this area. Well, guys, you're supposed to see that here we don't really have flat parts, right? But if you consider a little tiny square on this round sheet, this tiny square is almost flat, and you can make an area vector same way for this tiny square as you were using for a big flat piece of paper, right? Just gonna be tiny vector. And because all these flat little squares are kind of in different directions, all these vectors are going to be in different directions, okay? That's all about the first exercise. And I'm going to move to the last exercise. Exercise 2, or like part 2, does not require doing any experiments, but like exercise 3, which is like part 3, is going to require some experiment. So give me a second. Okay, for part which is part 3 flux, we are supposed to have a board with nails. I don't have big nails at home to make a board with nails. So I used actually thin spaghetti and Play-Doh to create a similar board. I have like 8 spaghettis vertically stick to this Play-Doh on each side. So it's like 64 in total of them. Well, I was trying to make them parallel as much as I could to make spaghettis. And I also made a frame. Let me show you the frame. Sorry, I'm making like the video myself this way. Kind of, I have to put camera somewhere on the holder. So that's a frame, which kind of goes for the area. Just imagine that area over here inside of the frame is transparent. And they are asking you like, in question B, obtain a wire loop. So this is going to be my wire loop. I don't have a wire loop, so that's the best I made so far. And that's going to be the boundary of the area. So actually area is inside, it's invisible, and this is just the boundary of the area. And they're asking you like, what is orientation of the loop to catch as many of this, well, nails, spaghetti, or like what is the orientation of the loop to catch like minimal amount? Well, you probably see that we can catch all of them if we put my area like perpendicular to spaghetti. Remember that area vector actually here is perpendicular to the area itself. So area vector is parallel to spaghetti. This is my area vector. I'm sorry, kind of hard to show everything. You put the camera a little bit away, maybe, yeah, this way. Okay, this is my area vector. This is my area, and these are my nails, which represent electric field. So I can catch maximum all of them, actually 64, if I put my area perpendicular to spaghetti and area vector parallel to spaghetti, right? Well, how do I catch less? Well, if I incline it, I will catch less, less, less. And eventually, when I make it vertical, I'm going to catch nothing. It just goes between the, like, spaghetti nails, right? Goes between and it catches nothing. So what happens to the area? You can describe it like area vector is directed a certain way to the spaghetti, right? For the next page, they are asking you to do counting of spaghettis, well, sorry, the nails, if you do different angles for the loop. Well, guys, I'm not gonna do many countings. I'm going to do maybe like, well, just maybe few. So they are asking you to place a loop over the nails at a number of the field lines through its maximum. Well, we already know that it's going to be something like this, and I can tell you that it's 64 because I just placed over here 64, the maximum, right? And they're asking you to rotate the loop. What I'm going to do, guys, I do have a protractor. Oh, sorry, my camera is shaking. I do have a protractor, and I'm going to make maybe 3 different angles for the loop and count the spaghettis and tell you the numbers. You record these numbers. You're not going to fill the table because my spaghettis are not parallel, and no one is helping me to do this experiment. If somebody was helping me, maybe I would do like more counts. So we already know that when the angle is, well, 0 between area vector and spaghetti, we count the maximum 64, right? Okay, guys, what I did is kind of a little bit different way to set up protractor because it's very hard to do everything with one hand. So again, I'm going to tell you approximate amount of spaghettis which the loop catches at certain angles. So angle is equal to 0 with horizontal line. Horizontal line angle is equal to 0. So actually the lines of spaghetti and the vector are parallel. So we are going to catch 64. 64, like all spaghettis, are sitting inside of the loop. Now, guys, what I'm going to do, I'm going to cut off one line of spaghettis, which is like 8 spaghettis. So 64 minus 8, 56, right? And see what is going to be the angle. My spaghettis are not very much lined, but what I see is that the angle is about like 30 degrees. The angle which I'm making with my loop, about 30 degrees to catch 56 spaghettis. Now I'm going to cut one more line and I'm going to catch 48 spaghettis, and the angle is about like 40 degrees. And then I'm going to cut one more, maybe 2 more lines and like catch 32 spaghettis. And for 32 spaghettis, I have the angle about 60 degrees. I don't know if you can see, like 60 degrees, kind of catching 32 spaghettis. And I'm going to do just last angle, like 80 degrees. And 80 degrees looks like it's catching only one line of 8 spaghettis. And you can just write it down. All the numbers here are approximate. Again, with nails, it's more accurate because nails are sturdy. My spaghettis are moving side to side and nothing looks very good. But you see the idea, right? So the loop catches more spaghettis when it's kind of exactly perpendicular to them. And when it's parallel to spaghetti catches nothing, and somewhere in the middle you have different numbers. Actually, these numbers are going to be described by a trigonometric function of cosine of the angle between like the lines of spaghetti and perpendicular to the area. Okay, well, again, you can repeat my experiment at home. It's not difficult to find Play-Doh or anything sticky and put some spaghettis and just try it on yourself. But if you kind of don't have time or just don't have spaghetti or nails or whatever, or loop, you just can use my results. So let's kind of repeat them. So for angle of 0, we have 64. For angle of 30 degrees, we have 56. For angle of 40 degrees, we have 48, and for angle of 60 degrees we have like 32 or about this, and for angle of 80 degrees we have just 8. well, they're not going to sit exactly on a very nice curve, but, just like, to see approximately how it works. Okay, thank you. That's all for this demonstration.